Hey everyone, welcome back. So today we're going to be talking about a special type of neural network called the recurrent neural network. Now let's go into it by talking about a specific problem, just so we start from something real. Let's say that we're designing some kind of website, and that website has a search bar at the top where our users can come in and search for whatever they want. And to make the user experience as easy as possible, we want to implement some kind of autocomplete. Just like on Google, you start typing your query and Google will automatically suggest some things that make sense given the words you've already typed. So for example, let's say the person has typed 3 words so far, how to make. We want to design some kind of model that is intelligently and automatically going to know that the next word is more likely to be pizza rather than yoga. And so we have a bright idea. We just finished learning about typical neural networks, and we think about, can we apply a neural network to this problem? So that's our bright idea. Now this is a really good starting point because anytime in data science or otherwise, you typically want to start from the things you know and only go to more complex or more intricate things if there's a reason to do so. So that brings us into the next topic, which is what are the drawbacks in terms of typical neural networks that we learned so far that are going to make applying those typical neural networks to this problem a little bit tricky. And there's 2 big ones. The first one is that typical neural networks cannot take into account variable sequence or input length. So for example here, I explicitly said the person's typed in 3 words, and we're trying to use those 3 words to make a good prediction about what word will come next. But of course, any good autocomplete method shouldn't be just using 3 words. It should be able to use 1 word or 2 words or 3 or 4 or 5, however many words the user has chosen to give us. Our model should be able to dynamically use however many words that is in order to give us a good recommendation for the next word. And with typical neural networks, it's not super easy to force this kind of problem into that setup. And so that's going to be one of the drawbacks there. The other big drawback is that typical neural networks don't really have a built-in notion of the directionality of the inputs. And you see this problem here, which is a natural language processing problem. But more generally, it is a problem where the order of the input sequence matters. For example, when we process this, it would make the most sense to process the first word, how, use that information to process the next word, to, use all of that information to process the next word, make, in that specific order in order to have the best prediction of what the next word should be. We definitely wouldn't get as good results if we chose to just process these words in any random order. And again, typical neural networks don't have a notion of the order of the inputs you're passing in. And for those 2 big drawbacks is where we bring in the solution of using recurrent neural networks. Now I'm about to start talking about this diagram that's behind me, but the main thing that I want you to remember through the course of this discussion is that we're not learning anything fundamentally new. I think it's always a little bit comforting when you learn a new topic, quote unquote new topic, but their pieces of that topic are basically things you already know from something you've learned previously. It's a lot less intimidating that way. And so we'll be using a lot of the same terminology we've been using in previous videos: inputs, outputs, activation functions, hidden layers. It's just that we're repackaging it in a slightly different way to make it able to solve these sorts of problems. So now let's go into how a recurrent neural network actually works, how it processes its inputs into outputs, and how we use all that to solve problems like these. So this diagram may look a little bit intimidating at first, lots of symbols and steps going on, but let's tell it as a story, which actually works out really well for recurrent neural networks because we use recurrent neural networks to usually solve sequential modeling. And so that pretty much lends itself to telling this sequential story. We start our story down here, and actually there's kind of a step 0 we should address, which is that you'll notice that the inputs we have right now are English words, and to do any kind of data science, data analysis, we need vectors, we need numbers. How do we take these words and turn them into some kind of vectors? And there's not one answer here, so let me give you a couple of options that you could do. One pretty out-of-the-box option is to use embeddings or vectors for words that already exist on the internet that were pre-trained on very large corpuses of data, usually Wikipedia or books or something like that, and just say, well, those seem smart enough, I'm going to use the same ones for my problem. So this is in the realm of something called transfer learning, where you use some kind of information learned via a different task, a different but related task, and hope that'll work well for your task too. Now, a more targeted approach would be to learn these vectors along with the model itself. I consider this a bit of a more advanced topic, and we won't say anything more than that here, but that is one option that may be more targeted to your specific problem. And what we'll be doing today is even simpler than both of those. which is that we'll be assuming each of these vectors, x1, x2, x3, x4, however many words we're processing, is a one-hot encoded vector. All that means is that each of these vectors is going to be a big vector of mostly zeros, except it has 1, 1 in it somewhere. And that 1, 1, the position of that 1, 1 tells you which word we are actually looking at right now. For example, if the word how was the first word in our vocabulary, then the one-hot encoded vector x1 would look like 1 followed by a ton of zeros. If 2 was the second word in our vocabulary, then that one-hot encoded vector would look like a 0 with a 1 followed by all zeros. So this is definitely not the most efficient way to encode your data because the size of this vector is going to be like the size of your vocabulary, but it'll serve us well because that's not the main focus of this video. So we'll just pretend that these are one-hot encoded vectors today. So now that we have step 0 out of the way, we can actually get into how our recurrent neural network is going to process these inputs. And so the first thing that happens is we take this vector x1, which again represents the word how, and we pass it through a linear transformation u. So u is a linear transformation or a matrix, whichever is easier for you to think about. We apply that linear transformation to x1 in order to get h1, which is the hidden state. So you see the same terminology popping up, which is the hidden state at the first time step. So the h says it's a hidden state, the 1 says it's at the first time step, or the first word that we're currently processing. Now the next thing that happens is that we apply a different linear transformation w to that h1 in order to get our first output vector, which is y1. Now I'm being a little bit loose with all the math here. I'll be more concrete when we talk about the math itself, but when I say a linear transformation, I'm also implicitly saying there is a activation function, these sigmas applied afterwards. So when I say linear transformation, please take it to mean linear transformation and then an activation function, just as we do with typical neural networks. And so after we've done that, we have y1. Now y1, what is y1 in the context of this problem? y1 is the neural network, the recurrent neural network's answer about what it thinks the next word should likely be if the only word the user has typed in so far is the word how. So I've typed in how, and I say what should the next word be if that's all I've seen so far, and the recurrent neural network, after all these weights have been learned, the answer is y1. And so explicitly y1 is also a vector, which is the size of our vocabulary, and the highest number in y1, the index of the highest number in y1 tells us what actual word should be predicted. And the reason that works out is if we kind of fast forward for a moment down here, you can see y1 is achieved by applying some kind of activation function, maybe a sigmoid. And so therefore we can interpret everything in there as probabilities. And so the biggest number in there is going to be the most likely next word, the index of the most likely next word. And so again, this part of the story, maybe I'm spending too much time on this, but I want to be very explicit, which is that if all we've seen so far is the word how, the model says, I think the next word should be y1, and that's the top autocomplete suggestion we would suggest to the user. But of course, as we were saying before, we've seen more than just the word how, we've seen a couple of more words. So how does the story progress from here? Well, that gets us into this part of the diagram, and let's focus now on the hidden state at the next time step, which is h2. How do we get h2? You'll notice there's two arrows coming into h2. The first one is that it's a linear transformation of the hidden state at the first or previous time step, h1. And so the first thing we'll do is apply a different linear transformation v to h1. We add that to this linear transformation of the next input word. So x2 gets u applied to it. And so we take u times x2. We add that to v times h1. And that is exactly how we get h2. And of course, there's the activation function that we apply there. So we can actually talk about the equation while talking about the diagram. I think that makes more sense. So again, u times x2, that's this piece right here. We take v times h1, that's this piece right here. Notice there's a t-1 subscript. So we're saying, hey, to get the hidden state at the next time step, please consider the hidden state at the previous time step. And also consider the current input. That's why this t and this t match up, but this is a t-1. And there's also a bias term, b sub h here. We run all that through some kind of activation function, and that's how we get h2. But forget about the math for a second. What is h2? Why have we created this hidden state at the next time step? This is encoding, if you notice, if you kind of follow the arrows, h2 is encoding information about the sequence so far, which is not very exciting. It's just one word. So it's encoding information about the sequence so far, and also the next thing in the sequence we just saw. So that you can think of this thing, you can think of this vector h2 as a representation of the entire sequence so far. And using that representation of the entire sequence so far, we apply the same linear transformation w that we did before, and we get y2, which is going to be the model's best prediction of what the next word should be, if the only words we've seen so far are now how to. And so if we've trained the model well, it should be more likely that this next word is the word make, because how to make is a pretty common phrase. And it should be a lot less likely that the next word is pizza, because how to pizza doesn't really make any sense. And we just keep going. Hopefully you're starting to see the point now, but there's nothing really new coming up in the next one, but let's continue the story to make sure we got it. The next thing we would do is say, how do we compute the hidden state at the third time step, which is h3? Follow the arrows. One thing that happens is that we apply the same linear transformation we did before, v, to h2. We add that to the same linear transformation we saw before, u, to this third input vector, x3, and those two things together is how we make h3. Again, the equation to get h3, you would take x3 and apply u, that's this going on right here. You would take h2 and apply v, that's this right here. Again, you have your bias term, you run that through some kind of activation function, and you have yourself the hidden state at the third time step, h3. And again, that's the math, but what is the intuition? Why are we doing this? h3, following all the arrows again, is capturing all the sequence so far. How to? Why is it capturing all the sequence so far? Because of this horizontal arrow, h2. Because h2 itself has captured the sequence before that. So h2 is containing all this information, has encoded information about how to. And then we also add that to the new information we're seeing at this time step, which is make, so that h3 can be thought of as a embedding or representation of the entire sequence how to make. And again, just like before, we run that through w, so that's this going on down here, so w times h3, we add its own bias term down here. We run this through an activation function. And just a quick note, I called the sigma sub h and sigma sub y because those activation functions don't have to be the same. One could be a tan h and one could be a sigmoid, for example. So they could be the same, they could not be the same, up to you. And we get y sub t, in this case y sub 3, which is, just like before, the recurrent neural network's best guess about what the next word in the sequence should be. And so going back to our intro example here, it should be much more likely that the recurrent neural network says the next word is pizza versus yoga, if all has been trained well. And that's it. Hopefully this story is kind of starting to make sense. And also hopefully you can extend the story to even more words. For example, what if I saw how to make pepperoni? The person typed in how to make pepperoni. All we would do is just add another one of these blocks over here. We would have an H4 and the exact same things would be going on. And hopefully after that, we have even more evidence the next word should be pizza, because pepperoni pizza makes even more sense than some other food like pepperoni popsicles. So in a nutshell, that's literally what a recurrent neural network is doing. We're just sequentially processing our inputs. The hidden state at each time step is collecting or encoding information about the sequence so far, and also taking into account information about the current word or current data point that's being seen at this time step. And so here's your diagram and here's your math down here. So let's just talk about the math explicitly. I think it's been pretty much covered, but again, to get the hidden state at any time step, you are going to first take this linear transformation u, so that's all these u's down here, process the current input, xt. You're going to add that to a linear transformation v, so that's all these horizontal arrows you're seeing here, times the hidden state at the previous time step, the value of the hidden state at the previous time step. That's why there's a t minus 1 right there. Add that to your bias term, run that through your activation function, and boom, you have your encoding of the entire sequence thus far. And then if you want to get the most likely next word, you're going to apply this other linear transformation w to the hidden state so far at the current time step. Add that to its own bias term, run that through an activation function, and boom, you've got your y sub t, which is the output at any time step that tells you what the most likely next word should be. Now this version of the recurrent neural network we've drawn here is often called the unrolled or unfolded version. And it gives you a pretty good look at the mechanics of everything that's going on that lets us talk about step by step by step. But there's also, you'll often see in the literature, a folded compact version, which looks like this. Because you might have noticed that there's nothing really new going on from block to block to block, from time step to time step. So to make everything more concise, people will often just draw the entire neural network as this diagram here, which captures all the relevant information. So this diagram is saying, given some input xt at any time step, we apply the linear transformation u, and then we also, the key part of the recurrent neural network diagram is this recurrence arrow, which says apply v to the value of the hidden state at the previous time step, ht minus 1, and those two things together give you h sub t, which is the value of the hidden state at this time step t. And finally, if you want to get the output at this time step, you would apply linear transformation w, go through all the activation function stuff, and you would get y sub t. So this tells the exact same story as this, just in a much more compact form. And there's this other thing I wanted to talk about too. The unrolled or unfolded form is of course nice to understand exactly what's going on, but it has this unfortunate property that people often think about H1, H2, and H3 as separate layers of the network, and it's not people's fault when you're learning this at first, because if you think about the diagrams we drew for typical neural networks, they look an awful lot like this, kind of drawn horizontally from left to right. And each thing, as we move from the left to the right of the page, are different layers in the neural network. And so it can be really tempting to say, H1 is the first hidden layer, H2 is the second hidden layer, H3 is the third hidden layer. But that's not right. And it's not just one of these technical things. I think it's important enough for me to actually write this on the board. Okay, I couldn't really find much room, but it says right here, H sub t are not layers, okay? Each of these is not a hidden layer. There's only one hidden layer. And so we have to read that from bottom to top in this case. Because think about what the purpose of a hidden layer was when you first learned neural networks. It was something between your inputs and your outputs. It was some kind of intermediate step, and we can have many of these intermediate steps if we want. But if you look at where your inputs are, they're down here. So here's your inputs. Where are your outputs? They're up here. And count the number of layers between your inputs and your outputs. There's only one layer here, H, right? You could put more if you want to make this more complicated, but the way we've drawn it here, there's only one hidden layer between your inputs and your outputs. So the correct way, and I've been trying to choose my words very carefully to make sure I don't slip up, so if I did, I apologize in the video, but each of these, H1, H2, H3, are not hidden layers themselves. They are values of the hidden layer, of the single hidden layer, at different time steps. So explicitly, H1 is the value of the hidden layer at the first time step. H2 is the value of the hidden layer at the second time step. H3 is the value of the hidden layer at the third time step, and on and on and on, okay? And the folded version does a lot better job of this, because you can literally say inputs, hidden layer, outputs. And so it's just that the hidden layer can take on different values based on what the value of t is, at which time step, or which position in the sequence that we're at. You probably noticed the applications of recurrent neural networks. The whole video was one particular application of autocomplete. But in general, anytime you have sequential or time-based data, recurrent neural networks and all of the more complicated things that come from them are very, very powerful models to use. And so I've just put two examples here. These are kind of like classes of examples. There's lots of sub-examples under here. So natural language processing uses recurrent neural networks a lot, both in the vanilla form we've talked about here, and also all the variations that we'll hopefully talk about in the future. And why does that case? Because when you think about language, any kind of language really, it is sequential. The thing that you say next depends a lot on the things you've said before. It's not like every word is random in any case, and the order matters a lot. So these two things, hopefully you can see now, have been addressed. The variable sequence length, as we have in language. If you say now the sequence is 2 terms longer, you can just add 2 more of these blocks and you can address that really well. And by the way, why are you able to address that? It comes down to the fact that these linear transformations, u, v, and w, you might have noticed they're the same at every time step. And so one natural thought is, wait, if you want to tune this network really well and you want to be able to have more flexibility, shouldn't you have a unique U, V, and W per time step? Like this should be U1, V1, W1. That should be U2, V2, W2. That would give you more flexibility, but it would not let you allow you to do this variable sequence length. Because if in your training data you've only seen sequences of length 5 or less, and now in the real world someone types 8 words, well, it's like, what should that U, V, and W 6, 7, and 8 be? It's unclear. And so, but if they are the same, as is implied by this folded version, then if you have some input sequence length you've never seen before, all you need to do is just append a couple more of these blocks, a couple more time steps, and you're using the same U, V, and W as we did before. So that's why they are the same. Anyways, I think I got off topic, but yeah, we were talking about applications to natural language processing. So with any kind of language, the sequence length can be variable, can be short sentences to large paragraphs, and also the directionality, of course, matters. People talk about things in a logical progression. The other big example is for time series. We talk about time series so much on this channel, but we've mostly stuck to using the ARIMA family of models. So autoregressive, moving average, all these sorts of things, which are interesting. But then there's also the case of, hey, why don't we try applying recurrent neural networks, which, as we just learned today, are able and designed to deal with this time-based sequential data and take into account the history of things that have happened in the past. So any kind of time series-based data is also a great candidate for recurrent neural networks. Now, let's close the video out by talking about the issues or the drawbacks of recurrent neural networks. We have to talk about all sides on this channel. One of the biggest ones is computation. So if you think about typical neural networks, just kind of thinking at a rough level, a lot of that can be parallelized. And the reason it can be parallelized is that we don't have any kind of notion of directionality of inputs, which intuitively just means that there's less dependencies of some data point on other data points, whereas here we have built the model to have dependencies, which is kind of a double-edged sword, because on one hand, these dependencies let us take into account the more interesting contextual historical representations of sentences and time series. So for example, if you look at H2, it takes into account information about H1, which is exactly what we want. But from a computational point of view, it also means that we can't have the value for H2 until we've processed the value for H1. Those two things cannot happen in parallel because one requires the output from the last one, which doesn't mean people haven't tried or even succeeded at this point in time to parallelize many parts of the recurrent neural networks. It's just that it is much trickier to do things like that computationally than with typical neural networks where there's a lot less dependencies between certain inputs. And another way to see at a high level this computational issue is when you think about how do we actually learn the weights in the network. So we have 3 sets of weights. We have U, V, and W. And as we learned with the neural networks video, we typically just use backpropagation. So that was the typical idea. Here, if we try to use backpropagation, so if I have a loss function L and I'm trying to find what should I update for the weights U, I would do something like derivative of the loss function with respect to U, just like that, right? And what would computing that entail? I would need to look at everywhere in the recurrent neural network where U gets used. So it's used here, here, here. Actually, it's used at every single time step. So I need to think about how a change in U at every time step is going to affect the final loss function, which means I have to take into account all of the time steps, which can be a bit of a computational burden. So there's a specialized type of backpropagation called backpropagation through time, BPTT, of course not going to be talked about in this video, which is designed to deal with things like. But it does make our lives a little bit trickier because updating these weights does require you to consider all of the time steps in the network all at once, which can be a bit of a computational burden. Now, one of the other issues here is that a vanilla recurrent neural network, as the one we looked at here, when people say vanilla in data science-y things, I don't know, it's a weird term. I've tried not to use it, but they just mean the most like basic version of some kind of algorithm or method. So in the most basic version of recurrent neural networks, it is one directional. So you notice that we have arrows going from left to right, but no arrows going from right to left. And so that's not something we can't fix. People have obviously tried to fix this because when you think about language models especially, language does not just flow from left to right, but there are many use cases for you to want to flow the language from right to left, or whatever is the natural flow in your language. You want to go the opposite way because you want to consider things not just earlier things in the sequence affecting later things in the sequence, but also how later things in the sequence are referencing earlier things in the sequence. So a lot of variants of recurrent neural networks will also throw in these backwards arrows, which makes this computation problem worse and more difficult to solve, but does give us more flexibility in bidirectional modeling, basically. And the final issue I want to talk about is a very interesting one too, which is the vanishing gradient problem. And so you're thinking, wait, I've heard about this for regular neural networks too. And yeah, it's not just a problem for recurrent neural networks. It's of course a problem for regular neural networks too, but it has a very interesting interpretation in recurrent neural networks, especially these language models. So if you remember back to our vanishing gradient video, which I'll link in the description below, the gradient of the loss function with respect to the very early weights in the network tends to 0, vanishes as the network gets bigger and bigger and bigger if we haven't done anything to address this. The counterpart here is that, let's say we're not just processing 3 words, but we're trying to process like a massive paragraph or book or something very large that has hundreds to thousands of words in it. And let's say we're again trying to compute something like derivative of the loss function with respect to u. That's going to require basically considering how u at every single time step, as we were talking about before, eventually affects the loss function. Part of that will involve answering how a change in h1 affects the final loss function. Well, for the piece of the loss function that depends on this prediction, y1, shouldn't be too much of a problem because there's only a couple of sigmoids or tan-h's, these activation functions there. But if you think about how the pieces of the loss function much later down the road, maybe hundreds to thousands of tokens or words down the road are going to be affected by h1, there's so many sigmoids and tan-h's and activation functions that it has to pass through to get there that its gradient for those is likely going to vanish. And what that means in intuitive terms is that the recurrent neural network kind of tends to forget or disregard information from earlier in the sequence because there's just so many steps that it has to go through. So in terms of language modeling, for example, if you have something much later in the sequence that should be referencing something very earlier in the sequence, there is a risk that recurrent neural networks will run into the vanishing or exploding gradient problem for those, if not dealt with properly. So anyway, this was just recurrent neural networks in a nutshell. There are many variations and branches and offshoots of recurrent neural networks that address these issues and try to do more fancy things, and hopefully we'll talk about them if there's enough interest. But if you have any questions at all, please leave them in the comments below. Hope you liked this video. Please like and subscribe if you did, and I will catch you next time.